When we wrapped up class last Thursday, I said the first thing that we were going to talk about today is comparing sinusoidal signals. So we're going to go ahead and jump straight into that. So one of the reasons that electrical engineers look at sinusoidal signals in particularly is because sinusoidal voltages and currents are effectively everywhere in industrialized nations that use AC power as their standard. And by comparing sinusoidal voltages and currents to each other, specifically to tell whether or not they are leading or lagging each other, can give us some information regarding the efficiency of these systems. So that's where we're going to focus on. So I'm going to put leading and lagging here. So before we can really get into the concept of leading and lagging, though, we need to establish a few base rules. Okay. So the first rule is that all waveforms must be expressed solely as sine or cosine functions. Because electrical engineers typically use the cosine function as their base, we are to convert all sines to cosines and leave all cosine functions alone. So let's say, for example, that we have a signal, let's call it VA of t, that is 12 cosine 16t plus 20 degrees volts. And we have a signal VB of t that is 8 sine 16t plus 130 degrees volts. In order for us to compare these two signals to each other, we would have to convert either the cosine function into a sine function or the sine function into a cosine function. We could do either of these based on the trig identities that I gave you guys at the end of our last class meeting. I'm going to convert the sine function into a cosine function. And just to refresh you guys, I do that by simply subtracting 90 degrees from the phase angle. So 8 sine 16t plus 130 degrees becomes 8 cosine 16t plus 40 degrees volts. The second criterion for us to compare our sinusoids to each other is that all waveforms must be expressed with a positive amplitude. So let's say, for example, that we have a third waveform of interest, Vc of t, and Vc of t is given as -5 cosine 16t minus, let's say, 90 degrees volts. To get rid of the negative sign out in front, we simply shift our phase angle by plus or minus 180 degrees. Does not matter which we choose. We're simply moving halfway around the unit circle to take into account that negative sign. And so that's going to look like 5 cosine 16t. I'm going to add 180, so negative 90 plus 180 is going to look like positive 90 degrees. And there's our third signal expressed with a positive amplitude. And then finally, our third criterion for comparison is that all waveforms must have the same frequency. And unfortunately, there's no trig identity that will allow us to correct for things if our signals have different frequencies. So there's no real example that I can do here to fix it. All right. So I'm going to try to plot these 3 waveforms. Okay. Bear with me here just a moment. So here's T. And then our vertical axis will be our voltage waveforms. So let's see, we have 12 with a phase angle of positive 20 degrees, which is going to indicate a shift to the left by some small amount. So let's put that here-ish. So that's where our peak is going to be. So this red curve is dA of t. Our blue curve is going to be VB of t, so that's 8 cosine with a phase angle of positive 40, which means we're going to have a little bit more of a left shift. So I'm just going to put that about right here. Something like this. And lastly, we have VC of t, amplitude of 5, phase angle of 90 degrees. So this is an even larger shift to the left. So let's put it roughly here. Something like this. So here's VC of t. So when we're looking at leading or lagging, we can say that a waveform leads another waveform if it hits its peak amplitude at an earlier point in time than the waveform it's being compared to. So in this specific example, the green curve hits its peak first, right? Because it hits its peak more to the left or earlier in time than either the blue waveform or the red waveform. So we could say that VC of t leads VB of t. We could say that VC of t leads VA of t. And since the blue curve hits its peak before the red curve, we could also say, that VB of t leads VA of t. In order for a waveform to lag, it needs to hit its peak value later in time. Peak, let me write it as amplitude, since that's what I used a moment ago. So for this specific set of 3 voltage waveforms, VA hits its peak last, so more to the right than the other two. So VA is lagging both VB and VC. And since the blue curve, VB, hits its peak later in time than the red curve, than the green curve, VC, we can also say that VB lags VC of t. Okay. Now, I personally often struggle with looking at these time domain graphs like I have here, where all of the signals are plotted as a function of time. They look a bit busy to me, and as I mentioned in our last class meeting, it can sometimes be a little bit confusing to realize that points to the left of the vertical axis means that we are at an earlier point in time with positive phase angles, and points to the right of our vertical axis mean that we are at later points in time, meaning that we have negative phase angles. So there is another method that we can use to look at these signals called a phase diagram that I personally prefer to use to determine leading or lagging. Okay. So in a phase diagram, effectively, we are just taking a snapshot of our signals at a specific time. And we're going to choose the specific time of t is equal to 0, because it means that we effectively just have a magnitude and a phase angle and we need no other information whatsoever. So I'm going to give myself a set of axes here. The positive horizontal axis is going to correspond to 0 degrees. The positive vertical axis will correspond to 90 degrees. The negative horizontal axis will correspond to plus or minus 180 degrees. And the negative vertical axis will correspond to negative 90 degrees. And so what I'm going to do now is I'm going to plot my three functions on this phase diagram. Okay, so VA in red, we had, let's see here, a magnitude of 12 and a phase angle of 20. So a phase angle of 20 would be something about like this. And I've just arbitrarily made it long to represent VA of T. VB of T was 8 units in magnitude and had a phase angle of 40 degrees. So 40 degrees should be somewhere about here. This will be VB of T. And then lastly, VC of T had a phase angle of 90 degrees, which means it's going to lie just on this vertical axis here. So here is VC of T. Now let's talk a little bit about how we read this type of diagram. All right. So as angles get more and more positive, we're looking at leading, and as angles get more and more negative, we're looking at lagging. So if we want to say by how much does VB of T lag VC of T, what we would start doing is we would start measuring from VC of T, and we would go in a clockwise direction for lagging. And we would see that we would have 90 degrees minus 40 degrees is equal to 50 degrees. So VB lags VC by 50 degrees. Similarly, we could say by how much or by what angle does VA of T lead VC of T? Since VC of T is the second thing in our expression, it's effectively our reference point. So we are going to start our measurement at VC. And because we're measuring leading, we are going to go counterclockwise. So we're going to start here. So we would have 90 degrees, another 90 degrees, another 90 degrees, and then 20 degrees. So 90 plus 90 plus 90 plus 20 is equal to 290 degrees. So VA lags VC by 290. Transversely, VC leads VA by 360 minus 290 would be 70 degrees. And we could have done that the other way as well. Okay. So this is how we use a phase diagram in order to determine the angle by which one waveform leads or lags another waveform. So just to really hammer this down, let's look at a problem from our web work really quickly. So I believe homework set 19, problem 2 involves leading and lagging. It does not, so it must be problem 1. Okay, yes. So we are asked to find the angle by which I1 lags V1 if V1 is given this specific figure, right? So let's look at part C in particular. Okay. So we're told that V1 of t is 194 cosine (120 pi t) minus 69 degrees volts. And for part C, I1 is given to us as -6 cosine 120 pi t minus 96 degrees. Amps. Since we have a signal with a negative magnitude, we would need to convert I1 of t into a cosine function with a positive magnitude. So that would look like +6 cosine 120 pi t. And if I add 180 degrees to -96, I believe I will get 84 degrees. So on my phase diagram, so again, we have 0, 90, plus or minus 180, -90 down here. Let's do V1 in red. So that's -69 degrees. So that's going to be somewhere around here. And I1, let's do it in blue, is going to be at 84 degrees. So that's going to be somewhere around here. And let's check what we're asked. Find the angle by which I1 lags V1. Right. So V1 is our reference point here. So we're comparing I1 to V1. Because we want lagging, we need to go in a clockwise direction. So if we start measuring from V1, we're going to have this much, which is 21 degrees, then 90, then 90, and then 6, right? So 21 plus 180 plus 6 is going to be 207 degrees. If my mental math is correct. If not, please pipe up and let me know. And what I'm going to do now is I'm going to put this into web work, and we're going to see if whether or not I'm right. So I believe I said the answer should be 207. Let's check things here. All right, so web work is telling me that I'm wrong. Now I'm fairly confident that I applied the process correctly, so I am going to actually double check my numbers to make sure that my mental math wasn't incorrect. But I believe I know why I'm getting the wrong answer here. So just for the sake of argument, 21 plus 180 plus 6 is 207. Okay. So one of the limitations of web work is that it doesn't understand that 207 degrees is the exact same thing as 567 degrees or negative 153 degrees, right? So if you follow the process that I have detailed and you're sure that your number is correct, what you should do is simply add or subtract 360 degrees from your answer, and one of those is going to be the one that WebWork accepted, okay? So I am just going to subtract 360 degrees here, see how this works out. And all of a sudden, my answer is now correct. So it is 207 degrees, but WebWork was expecting negative 153 because of the way that it was programmed, okay? So for these particular homework assignments, or for this particular homework problem, I guess would be a better way to put it, you can be working everything absolutely correctly, and WebWork will kind of throw you a curveball and tell you that you're wrong simply because it doesn't understand the equivalence between angles that are shifted by 360 degrees. Okay, so I just wanted to point that out for you guys because I understand that it can be frustrating when you're following along doing things right and WebWork doesn't particularly care for the way that you input your answer. All right, so before we move along to our next topic, are there any questions regarding comparing sinusoids and the concept of leading and lagging? All right. So now we are going to actually start analyzing circuits again. So I'm going to call this steady state sinusoidal circuit analysis. This is going to be our topic for the next several days. And today we are going to focus on looking at things in the time domain. And I'm going to go ahead and preface this by saying that we are going to see that looking at signals for circuits undergoing sinusoidal steady state in the time domain is going to involve a ludicrous amount of trigonometry and a fair amount of calculus. It's going to be difficult. I'm showing you this time domain relationship so that we understand why we're going to wind up using complex numbers to represent things, which will in turn make the math significantly easier. Okay, so fully aware that I'm about to hit you with 45-ish minutes worth of terrifying math with a full expectation that we will never ever do this again. So let's look at a relatively simple circuit. We have an AC current source that's going to give us some current IS of t, which I will define in a moment. And then we're going to have a 6 ohm resistor and a 2 Henry inductor, like so. And our ultimate goal is to determine the voltage drop across our source as a function of time. So let's first define IS of t. Let's say that it is 2 cosine 5t plus 12 degrees amperes. So this is our first example of a circuit that is going to be undergoing sinusoidal steady state. So I want to talk a little bit about what our expectations should be for our result in this problem. Okay. So when we dealt with DC circuits, and I can do something really quickly here. So this is a brief aside. You don't need to write it down. I'm probably going to erase it in just a moment. But if we looked at this circuit as a DC circuit, let's say that this current was 2 amps. Still had a 6 ohm resistor. And we still had a 2 Henry inductor here. And we were trying to find the voltage drop over our current source. What would it be? Anybody care to venture a guess? So since this is a DC circuit, we know that our 2 Henry inductor should be behaving as if it were simply a short circuit, which means that the voltage drop across the 6 ohm resistor is the same thing as the voltage drop across our current source. 2 amps times 6 ohms gives us 12 volts. So when we excited this circuit with a DC signal, our response was also a DC signal. So it should stand to reason that if we excite our circuit with an AC signal, like I have here, I would expect that Vs of t will be a sinusoidal signal as well, okay, or an AC signal as well. So I'm going to guess that Vs of t will be of the form Vm cosine 5t plus some phase angle theta v volts. Okay. So let's see if that shakes out. All right. So how I'm going to approach my analysis here is by recognizing that I have a single loop circuit. And so I'm going to start by applying Kirchhoff's voltage law. So I'm going to call this voltage the voltage drop across my resistor, VR of t, and I'm going to call this voltage drop across my inductor, VL of t. And I can say that Vs of t will be equal to VR of t plus VL of t. I know that VR of t is simply going to be I times R. So that's going to be 6 ohms times that 2 cosine 5t plus 12 degrees amps. And VL of t, so let's see, that's going to be L times di by dt. So that's going to be 2 Henrys times the derivative with respect to time of that current, 2 cosine 5t plus 12 degrees amps. So 6 times 2 is 12 cosine 5t plus 12 degrees volts. Let's see, so now I need to do the derivative of cosine. So if I'm not mistaken, the derivative of cosine is negative sign. So we're going to have a minus sign out here in front. I'm also going to have to apply the chain rule. So that means I'm going to pull a factor of 5 out because there's a 5 being multiplied by the t. So 2 Henrys times 2 amperes times 5 radians per second. 2 times 2 times 5 is going to look like 20 sine 5t plus 12 degrees volts. So just to be clear here, this bit represents the R of t, and this bit represents the L of t. So I have a result here, and it's kind of similar to what I'm expecting. But instead of a single sinusoidal function, I now have it as effectively the sum of two sinusoidal functions. So what I'd like to take a moment here to do is to plot these two functions on Desmos, which is an online graphing calculator kind of thing, and see that if I add those two together, do I get a single sinusoidal function? So I'm going to go to Desmos graphing really quickly. And let's call this first waveform y1 of x, and it is equal to 12 cosine 5. Let's see here. So what I am currently hesitating about, actually, let's just do it, x plus 12, right? So I have a little bit of a hiccup thing right here. It's not intuitively obvious, but because 5 is an angular frequency measured in radians per second, when I multiply that by time, I'm getting an angle in radians, and then I'm adding a phase angle, which is represented into degrees. So I either need to convert my phase angle, which is measured in degrees, into radians, or I need to convert that 5t into degrees in order for this to actually work out correctly. I'm going to convert my phase angle by simply multiplying it by pi over 180 degrees, so that both parts of my the argument of my cosine function are now expressed in radians. Okay. Y2, which will be the inductor voltage, is negative 20 sine 5x plus 12 times pi over 180. And I'm going to play with the settings here really quickly. Let's change the x-axis values. Instead of plus and minus 10, let's start at t is equal to 0. And let's go out to, let's say, t is equal to 4. And let's make our y-axis go from negative 25 to positive 25. All right, so I have these two sinusoidal signals plotted here. Let's see what happens when I add them together. So let's say that y is equal to y1 plus y2. And now I'm going to turn off these two. And it certainly looks like this is a single sinusoidal function, right? the magnitude of this sinusoidal function looks to be about 23.324 volts. The phase angle should be positive, and I'm saying that because let's see if we extend this x-axis to -1. Yeah. So our peak amplitude occurs a little bit before t is equal to 0. So this is a cosine function shifted to the left by some amount. Okay. So we should be expecting an amplitude of 23 and some change with a positive phase angle. Fourier series, well, so a Fourier series for a sinusoid doesn't exist, right? Fourier series are for non-periodic functions. There is a Fourier transform, but that would just give us effectively an impulse in the frequency domain, and we're not to that level of electrical engineering just yet to understand what an impulse in the frequency domain really means. So we're going to keep things in the time domain, and what we're going to do is we're going to use trig identities to try to sort this out and figure out how to come up with a relationship for the amplitude and the phase angle of this single sinusoid representation. So I'm going to refresh us on a couple of trig identities that I introduced in our last class meeting. I don't remember what the number I used for these were, but I gave you a trig identity that I think was cosine, let's call it alpha plus beta, is equal to cosine alpha cosine beta minus sine alpha sine beta. So that was one trig identity. I'm going to make one small change here. If we multiply cosine alpha plus beta by some arbitrary constant k, we should multiply the right-hand side of the equal sign by that same arbitrary constant k. I also introduced to you all a relationship that said sine alpha plus beta was equal to sine alpha cosine beta plus cosine alpha sine beta. I'm doing this from memory, so I'm 90-ish% that's percent sure that's correct. We'll run with that, and hopefully I won't embarrass myself too much if I'm wrong. And once again, if I multiply this guy by an arbitrary constant k, it's the same as multiplying this side by an arbitrary constant k as well. So we're going to apply this first trig identity to the VR relationship, and we're going to apply the second trig identity to the VL relationship. And so what that's going to get us is Vs of t will be equal to 12. So I'm going to call 5t beta. All right, let me show you this here real quick. So this is going to be beta, and this is obviously beta as well. And then this plus 12 degrees is going to be alpha, like so. So cosine alpha is going to look like cosine 12 degrees, And then cosine beta is just going to be cosine 5t minus sine alpha. So sine 12 degrees. Sine beta is going to be sine 5t. And then I'm going to have minus 20 sine 12 degrees cosine 5t plus, all right, my stylus doesn't want to write this plus sign, there we go, cosine 12 degrees times the sine of 5t. Okay. I'm going to expand this out a little bit. So let's call this 12 cosine 12 degrees cosine 5t minus 12 sine 12 degrees sine 5t minus 20 sine 12 degrees cosine 5t minus 20 cosine 12 degrees sine 5t. And now I'm going to lump some things together, right? So I could say that I have 12 cosine 12 degrees minus 20 sine 12 degrees multiplied by cosine of 5t. And I'm going to have minus 12 sine 12 degrees plus 20 cosine 12 degrees times the sine of 5t. So let me double check my signs here to make sure I'm not making any mistakes. So 12 cosine 12 degrees should have a positive sign. That's from this part right here. Then I should have negative 20 sine 12 degrees from this part right here. So that checks out. I'll have negative 12 sine 12 degrees times sine 5t from this guy right here. And then this term, because it's also negative, I just pulled that negative sign out and added these up as two positive quantities. Okay. All right, so it seems like everything's going okay thus far. So 12 cosine 12 degrees minus 20 sine 12 degrees is literally just a number. So I'm going to put that in my calculator. So making sure that my calculator is in degree mode, 12 cosine 12 degrees minus 20 sine 12 degrees gives me a number 7.5795 and some change. So I'm going to call that 7.580 cosine 5t. And then 12 sine 12 plus 20 cosine 12 is also just a number. So let's put that in. So 12 sine 12 degrees plus 20 cosine 12 degrees is 22.058. So minus 22.058. sine 5t. Okay. So we've done, looks like 1, 2, 3, 4 steps here in the application of two trig identities to get us to still the sum of sinusoidal functions, but we've somehow managed to get rid of the phase angles, okay? Now this might seem odd, but this is actually a really good place because effectively what we're going to do now is we're going to work on applying this trig identity backwards, right? We have something of the form of the right-hand side, and we're going to figure out how to work backwards to get to the left-hand side, okay? So that means that, let's see, so I said 5t was beta. So I have something cosine beta here, which means this thing right here must be k cosine, I don't want to call it alpha. This will be theta v. And actually this k will be Vm, the magnitude of our voltage. And then I have minus k sine alpha sine beta. So this guy right here is going to look like Vm sine theta v, if I'm not mistaken. Trying to remember whether or not I'm going to mess things up with a negative sign here, but I believe it's going to work out okay. We'll see in a moment. All right. So let's hit you with another couple of simple-ish trig identities, right? So if I have Vm cosine theta v squared plus Vm sine theta v squared, that would be the same thing as Vm squared cosine squared theta v plus Vm squared sine squared theta v, or Vm squared, since cosine squared plus sine squared is equal to 1, right? So from this, the magnitude of my voltage waveform should simply be the square root of Vm cosine theta v quantity squared plus Vm sine theta v quantity squared, or the square root of 7.580 volts plus negative 22.058 volts. Both of these quantities are squared. So throwing that into my calculator, I get 23.324 volts. So just to look at something really quickly here, let's go back to Desmos. Our peak value of this single sinusoid representation looks to be a little bit more than 23. So we are in good shape thus far. Okay. to find my phase angle, let's do this in purple. So I know that the tangent of theta v should be equal to the sine of theta v divided by the cosine of theta v. And it shouldn't hurt anything if I put Vm out in front of both of these quantities, right? So tangent is sine over cosine, if my trig identities memory is working correctly. So from that, theta v should be equal to the inverse tangent of Vm sine theta v divided by Vm cosine theta v, or the inverse tangent of, actually, I have a very slight mistake here that's not going to matter, but there shouldn't be a negative sign there. Because Vm sine theta v is just the 22.058. So my apologies for that. And then 7.580. So let's see here. The inverse tangent of 22 divided by 7.47. Sorry, trying to get fancy on my calculator and it's not catching what I'm throwing. I get 71.035 and some change degrees. So putting this together, Vs of t should be equal to 23.324 cosine 5t plus 71.035 degrees volts. So I got my magnitude right. I have a positive phase angle, so that's good. Let's plug this representation into Desmos and see if they're the same signal. So I'm going to have a new thing. 23.324 cosine 5t plus 71 point, oh, sorry, x plus 71.035 times pi over 180. The purple curve here, which is our solution, completely overlaps the green curve, which means we've done all this correctly. We have effectively figured out how to express the voltage drop across our current source as a single sinusoidal function. Okay. Now, I know for sure that what I just did is an overwhelming amount of math for most of you guys, right? This circuit, let's look at it really quickly here, was a fairly trivial circuit. We had a single source, a resistor, and an inductor, And I'd be willing to bet that it took me somewhere in the ballpark of 35 minutes to do all of this math, applying these trig identities and all this kind of stuff. If we added even another resistor to this circuit that was, say, in parallel with a 2 Henry inductor, the amount of math that we would need to solve it would be absolutely ludicrous. Okay. So I want us to do a little something else here, okay? Let's say that this voltage VR of t was the complex number 12 angle 12 degrees. And let's say that we represented VL of t as 20 angle, let's see, 12 minus 90 degrees, because I'm converting that sine to a cosine function. So 12 minus 90 should be negative 78. So what happens if we put 12 angle 12 degrees minus 20 angle negative 78 degrees into our calculator and have our calculator give us the result in polar form, right? So let's write this down here. So 12 angle 12 degrees minus 20 angle negative 78 degrees. Putting this in my calculator. I get 23.32807 or 323807. So let's call this 324 with an angle of 71.036 degrees. So effectively, this is the same thing as this, or at least we got the magnitude correctly and the phase angle correctly, except for a tiny amount of rounding error here. We got the exact same result, at least for the magnitude and phase angle, in mere seconds compared to the 30 plus minutes of trig identities and all of that kind of garbage that I had to do to solve this problem in the time domain. Okay. So what I'm going to do now is try to explain to you why I can do this using complex numbers. So if we have a linear black box network, let's put some terminals over here to the left. This is where we're going to apply our input signal, and just for the sake of argument, let's call that input X of t. And over here to the right is where we're going to measure our output. Let's call it Y of t. And let's say that our input X of t is a sinusoidal current. I am cosine omega t plus some phase angle theta I. So this is exactly the input signal that we just used. And we found that our output could be expressed of the form Vm cosine omega t plus theta v, right? That was the generic form of our result. So we literally just proved that if we have a linear circuit, it will behave this way. So let's take this one step further. We're going to take that same linear black box network. We're going to apply an input. Let's call this x2, and I'm going to come back here and put subscripts of 1 here. And let's figure out what our output y2 is. So let's say that our input x2 of t, once again, let's make it a current, Im, but this time let's call it a sine function. So we have an input of Im sine omega t plus theta I. I would expect my output to be of the form Vm sine omega t plus theta I. So effectively, if I put a sinusoid or a cosine function at the input, I should get a cosine function at the output. Similarly, if I put a sine function at the input, I should get a sine function at the output. And that shouldn't be very hard to understand because we know that a sine function is just a cosine function shifted by 90 degrees, right? So we really haven't shown anything remotely new with this second identity. What I'm going to do now is I'm going to make a slight modification here, okay? So if you recall from our lecture on superposition, there was a thing called the homogeneity or scaling principle of linearity. And that scaling principle said that if I scale my input by some arbitrary amount, as long as it isn't time varying, my output should scale by the same amount. So what I'm going to do is I'm going to scale my input by a factor of j, our imaginary operator, which should in turn scale my output by a factor of j as well. So for this last step here, I'm going to apply the additivity principle of linearity. So if I have an input x of t, where x of t is x1 plus x2, or Vm cosine omega t plus theta v plus j Vm sine omega t plus theta v. I can use Euler's identity, which was one of the trig identities I gave you guys to work with at the end of the last class period. I can express this sum of sinusoidal functions as Vm e to the j omega t plus theta v. Well, my output will just be y1 plus y2. Sorry. Got these backwards. These should be currents. My apologies. This should be Vm cosine omega t plus theta v plus j Vm sine omega t plus theta v. And I can also express this as a complex number form as well, okay? But what's really, really interesting about this is that the real part of my input gives me the real part of my output, and the imaginary part of my input is responsible for the imaginary part of my output. So I can use a complex number, which will make the math easier, and then just only take the real part of the result. And that would be the exact same thing as if I had done all of those trig identities and stuff like that, working with the cosine function the entire time. So that's why this representation of just using a complex number, particularly the cosine portion or the real part of these signals and adding them together or doing the correct mathematical operation, in this case, the subtraction sign, winds up giving us the exact same result as if we had done everything using all of those trig identity, calculus relationships, and all that kind of good stuff. So before we move along from here, I want to look at another couple of things from your web work. All right, so we've talked about effectively how to do everything here for problem one, nothing particularly wild or crazy. Let's look at this thing right here, problem two, okay? So it asks us to find the magnitude of the sum of sinusoids, or effectively it's asking us to express this large quantity, 60 cosine 100t minus 115 degrees, minus 39 sine 100t plus 87 degrees, as the sum of sinusoids with no phase angle, or a single sinusoidal function, okay? Now, I have shown you, using all those trig identities, how we could get to both of these representations. Let's work this instead using strictly complex number relationships, okay? Scroll down here. Homework 19, problem 2. So 60 cosine 100t minus 115 degrees minus 39 sine 100t plus 87 degrees. And we want this to be equal to A cosine 100t plus B sine 100t, or C cosine 100t plus B. Okay. So this bit right here as a complex number would be 60 angle negative 115 degrees. This bit right here as a complex number would be 39 angle negative 3 degrees, right? Because to convert our sine into a cosine, we subtract 90 degrees. So if we take the difference of these two complex numbers, we would have 60 angle negative 115 minus 39 angle negative 3 degrees gives us 82.5 0.910 with an angle of negative 140.858 degrees. Let's look at something here. 82.910 negative 140.857. Those are the correct answers. You can see that my recorded score is 100%. Okay. So that simple bit there gave us this form. Now, how do we get this form? Well, if I convert that complex number 82.910 angle negative 140.858 degrees into a rectangular form complex number, I get negative 64.304 minus J 52.337. This quantity right here is A, and this quantity right here without the J is negative B. The reason it's negative B is because of this trig identity. We get cosine minus sine, but here we are explicitly trying to find cosine plus sine. Okay, so we can do all of these sinusoidal manipulation problems for all of this homework set using complex numbers and make it wildly more simple than going through all of those terrible trig identities and all of that kind of stuff. Okay, so I just wanted to make you guys aware of that. This homework set is going to look incredibly difficult, and it is, unless you use complex numbers. If you use complex numbers, it is extraordinarily trivial. All right, so yeah, let's keep going. So we are going to talk now explicitly about how to work in the frequency domain. Okay. So the frequency domain is the domain that allows us to use a simplified form of our complex numbers in order to apply all of the circuit analysis techniques that we've already learned to be able to analyze any steady state sinusoidal system. Okay, so the first thing that we're going to talk about very briefly here is the different domains. Okay, so we've seen that a voltage V of t of the form Vm cosine omega t plus theta v is the real part of the complex representation Vm cosine, excuse me, e to the j omega t plus theta v. Similarly, the current I of t could be Im cosine omega t plus theta I, and this would be the real part of a complex representation Im e to the j omega t plus theta I. Over here on the left, we have our time domain signals. And here we have what I'm going to call mixed domain signals. So they're somewhere in between the time domain and the frequency domain. To work in the frequency domain, we are going to use what are called phasors. And a phasor is nothing more than a simplified representation of these mixed domain signals that throws away redundant information. So our phasor voltage V is going to be denoted by having a bar over it. And it is going to be simply the magnitude of our time domain signal and the phase angle of our time domain signal, and everything else gets thrown away. Same thing for our current phasor. We're going to have simply Im angle theta I. So these are our frequency domain signals. Commonly known as phasors. Okay. So we've actually already done this a couple of times, but just to make things extraordinarily explicit, let's say that I have signal VA of t that is 14 cosine 9t plus 106 degrees volts. The phasor representation of this voltage would be VA is equal to 14 angle 160 degrees volts. We just take the magnitude, take the phase angle, throw everything else away. Anytime we have a cosine function, that's all we need to do. Okay. Let's say instead that we have a current, IB, that is 6 sine 22 pi t minus 11 degrees amps. We're going to need to convert this into a cosine function. So that would look like 6 cosine 22 pi t minus 101 degrees amps. And from there, sorry, IB would be 6 angle negative 101 degrees amps. Okay, we've just taken the magnitude of our cosine function, taken the phase angle of our cosine function, and thrown everything else away. That's all it takes to go from the time domain into the frequency domain. Represent your signal as a single cosine function, take the magnitude, take the phase angle, throw everything else away. Okay. So now what we're going to do is we are going to derive some frequency domain relationships for resistors, capacitors, and inductors. Okay, so we're getting back towards circuit analysis techniques here. So let's look at a resistor. Okay. here is our resistor R. This is our time domain voltage drop across our resistor R. This is our time domain current flowing through our resistor R. Let's say that our voltage V of t is generically of the form Vm cosine omega t plus theta v, which we know is the real part of Vm e to the j omega t plus theta v. And our current I of t is of the form Im cosine omega t plus theta I, where this is the real part of Im e to the j omega t plus theta I. So the relationship between current and voltage in a resistor is, as we all know, Ohm's law. Okay. V of t will be equal to R times I of t, always. What I'm going to do here is I'm going to substitute in those complex number relationships here, right? So that's going to give me Vm e to the j omega t plus theta v will be equal to R times Im e to the j omega t plus theta I. What I'm going to do now is I'm going to break those exponential functions up into two parts, right? So this left thing would be Vm e to the j omega t times e to the j theta v, because when I multiply those two exponentials together, their arguments are going to add, giving me this relationship. So these are identical. And now I'm going to have R times Im e to the j omega t times e to the j theta I. I can see that there is a common factor of e to the j omega t on both sides, so I can get rid of it. Effectively, I'm throwing away the redundant information, which is what allows me to get to phasors. Okay. So this leaves me with Vm e to the j theta v is equal to R times Im e to the j theta I. So before we move along from here, I want us to make a couple of observations. And these aren't particularly difficult to understand. Okay? On the left-hand side of the equal sign, I have an exponential form complex number. I have a distinct magnitude Vm and a distinct phase angle theta v. On the right-hand side of my equal sign, I also have an exponential form complex number, a magnitude of R times Im and a phase angle of theta I. So if I have a exponential form complex number is equal to an exponential form complex number, it should be easy to see that the magnitude on the left-hand side must equal the magnitude on the right-hand side, and the phase angle on the left-hand side must equal to the phase angle on the right-hand side. So effectively, we can say that Vm will be equal to R times Im, and we can say that theta v will be equal to theta I. So simple Ohm's law with the magnitudes will give us our regular relationships, and the phase angle of the voltage and the phase angle of the current through a resistor must be equal to each other. So effectively, a resistor does not introduce any sort of phase shift. Okay. So these are a couple of observations that we are going to utilize numerous times throughout this course. All right, so getting back to the left-hand side of the screen here, we should know that a polar form representation of, or we could represent both of these exponential form complex numbers as polar form complex numbers. So that would be Vm angle theta V on the left and R times Im angle theta I on the right. Well, this is nothing more than our phasor voltage V is equal to R times our phasor current I. So effectively, Ohm's law in the frequency domain is exactly the same as Ohm's law in the time domain, in DC circuits, in every other representation we have ever seen or will ever see. Ohm's law is just Ohm's law. Okay. So this is one of our starting points. Now let's look at what happens when we have an inductor. So here's our inductor, L, our time domain voltage across it, and our time domain current flowing through it. And we are going to use those same signals that we used earlier, right? So we know that for an inductor, V is equal to L times di by dt. Substituting in our complex representations of our time domain signals, this is going to give us Vm e to the j omega t plus theta v will be equal to L times the derivative of Im e to the j omega t plus theta I. So Im is a constant, so I'm going to pull that out. So I'm going to have L times Im, and now I need to take the derivative of that exponential function, right? So the derivative of the exponential function is the exponential function itself. So we're going to have e to the j omega t plus theta I here. Then applying the chain rule, we need to take the derivative of the thing that's the argument of the exponential with respect to time. And so that's going to give me a j omega out front. So effectively, anytime I take the derivative of e to the j omega t, that's the same thing as me just multiplying by a factor of j omega. Right? I'm going to expand these exponential functions again. So I'm going to have Vm e to the j omega t times e to the j theta v will be equal to j omega L Im e to the j omega t e to the j theta I. And once again, this common factor of e to the j omega t can be thrown away from each side. So this leaves me with Vm e to the j theta v is equal to j omega L times Im e to the j theta I. All right, so when we were dealing with the resistors, we had a exponential form complex number on the left-hand side and an exponential form complex number on the right-hand side. Right now, we have an exponential form complex number on the left-hand side and a rectangular form complex number, the j omega L, times an exponential form complex number. So we've got things a little bit mixed up or wonky here. So I want to get rid of that J at the beginning in order to see something here. So I'm going to show you guys something over here on the right-hand side of the screen. So this is my complex plane. Here are my real numbers. Here are my imaginary numbers. So if I go out 1 unit in the positive real direction, or the number that we would commonly call 1, that is the same as a polar form complex number 1 angle 0, a rectangular form complex number 1 plus j0, and an exponential form complex number 1 times e to the j 0 degrees. Well, if I go up 1 unit in the imaginary direction, commonly called j, this would be 1 angle positive 90 degrees as a polar form complex number. It would be 0 plus j1 as a rectangular number, and it would be 1 e to the j 90 degrees as an exponential form complex number. We could stop here because I figured out how to express j, but let's do this over here really quickly. If I go 1 direction, or excuse me, 1 unit in the negative real direction, that is -1, or 1 angle plus or minus 180 degrees as a polar form complex number, -1 plus j0 as a rectangular form complex number, or 1 e to the plus or minus j 180 degrees as a polar form, or excuse me, exponential form complex number. And then finally, going 1 unit down in the imaginary direction would be -j, or 1 angle -90 degrees, 0 minus j1, or 1 e to the minus j 90 degrees. So when I multiply by j, that's the same thing as me adding 90 degrees to my phase angle. So I could call this instead omega L Im e to the j theta I plus 90 degrees. So from here, I can see that Vm, my magnitude on the left-hand side, is equal to omega L times Im, my magnitude on the right-hand side. And I can see that theta V will be equal to theta I plus 90 degrees, which means our voltage is always 90 degrees more positive than our current. So in an inductor, we can say that the current lags the voltage by 90 degrees. And this will always be true for any and every inductor, okay? The current will lag the voltage by 90 degrees. All right, so I can express this Vm e to the j theta v as a polar form complex number. So Vm angle theta v will be equal to j omega L times Im angle theta I, or phasor voltage V is equal to j omega L times phasor current I. So this is our current voltage relationship for an inductor in the frequency domain. Lastly, we're going to talk about what happens when we have a capacitor. Okay. for a capacitor, where this is our time domain voltage across it, and this is our time domain current flowing through it, we know that I will be equal to C times the derivative of the voltage with respect to time. And using our complex representation, we're going to have Im e to the j omega t plus theta I will be equal to C times the derivative with respect to time of Vm e to the j omega t plus theta v. As we saw a few minutes ago, taking the derivative of the e to the j omega t is just multiplying by a factor of j omega. So this is going to look like j omega c Vm e to the j omega t plus theta v. My e to the j omega t bits are common to both sides, so I can throw those away, leaving me with Im e to the j theta I is equal to j omega c times Vm e to the j theta v, which is the same as omega c times Vm e to the j theta v plus 90 degrees. So I can see that Im will be equal to omega times c times Vm. I can also see that theta I will be equal to theta v plus 90 degrees, which means our current leads our voltage by 90 degrees, always, always, always for a capacitor. I can express these exponential form complex numbers as polar complex numbers. So that's going to be angle theta I will be equal to j omega c times Vm angle theta v, which means I have phasor current I is equal to j omega c times phasor voltage v. So those are my relationships for a capacitor. We only have 6 minutes left of our regular class meeting time, and that's not enough time for me to talk about the concept of impedance just yet. So the very last problem of the in-class assignment for today's stuff, you actually won't be able to do just yet. That'll be the first thing that I'm going to talk about on tomorrow's class meeting. I've talked for 105 minutes straight. Do you guys have any questions before I end your suffering for today?
I will be in touch.
I'm sorry, what was that?
I will be in touch.
All right.
Yep. It
sounds good.
It seems like there are a lot of identities. We kind of just derived a lot of these concepts today, but it seems like in the end we can use these identities. You want to call them identities for some of the problems. Is that true?
Very much so. And what we're going to do at the very beginning of class on Tuesday or tomorrow is we are going to define the concept of impedance. Impedance is going to play the role of play the role that resistance did in our DC circuits. So what my goal here is to take these time domain steady state sinusoidal circuits and give us the tools to convert them into the frequency domain so that we can effectively just do simple DC circuit analysis to get our AC results. Okay, So for things to be a bit confusing right now, perfectly reasonable, because I'm not quite finished yet. But once we talk about the concept of impedance, we'll actually be able to tie everything together and then apply simple techniques, Ohm's law, KCL, KVL, voltage division, current division, things like that, that we've been doing to these complicated AC systems, and really just do all of the exact same analysis that we've been doing previously. Now we're just using complex numbers.
So it's kind of like we worked out integration by hand, but before we learned the power rule. Is that a good analogy? As to
Yeah,
we learned how it works.
Another way to think about things is we, instead of I don't know how familiar you are with like differential equations and all of that kind of stuff, but effectively, instead of solving differential equations by hand, we are learning the Laplace transform, which is going to make our life a lot easier. And that's actually kind of exactly what we're doing.
Okay, great.
Yeah.
All right. That's all I've got. Thank you so much.
No problem. I'll see you tomorrow.
All right, take care. Bye.
Yep.